Welcome. I want to share with you today some recent research activities that are ongoing in our lab, the Dependable Computing Systems Lab. My name is Saurabh Bagchi. I'm a professor in electrical and computer engineering and computer science here at Purdue University. So right there in the name of our lab is the word dependable computing. So let's try to tease apart what this means. So in our professional lives, personal lives, we have computing systems that we use to make our lives easier, more efficient, and as these systems are becoming more critical in our daily operation, we need to be able to depend on the operations of these computing systems. And we need to be able to depend on the operations of these computing systems despite the presence of naturally occurring faults, things like hardware malfunctions or software bugs. These are the unintended faults or unintentional faults that are put in our computing systems. And we also need to be able to tolerate maliciously introduced intrusions or attacks. And these could take the form of either an insider attack, so a user who's already a part of the system inside the periphery of the system, or an external adversary who's outside. And dependability, simply put, is the property that our system continues to provide its specified functionality despite the occurrence of these kinds of failures. And it needs to provide this functionality not only correctly but also within the required time bounds. So at the Dependable Computing Systems Lab, we develop, design, and implement different kinds of dependability mechanisms. For the most part, our dependability mechanisms operate in software, at the application level software or the middleware level software, or in the case of our embedded systems work, at the firmware level software. Then these mechanisms that we have developed, we introduce them in practical real-world systems, working closely with domain scientists in the area of high-performance computing, computational genomics, web-based software, web services, in the context of large-scale software that operates on our industrial control systems. And then we evaluate these mechanisms in practical settings by injecting error at higher rates and also by injecting different kinds of attacks, including attacks which are propagating out in the wild today. So who we are 14 graduate researchers currently, 3 research scientists and 5 undergraduate researchers working quite closely together in various projects. Our projects tend to have multiple participants, anywhere between 3 to 8 participants in them, including faculty, students, and research scientists. And we are part of 3 centers at Purdue: CRISP, where we have the leadership role. This is a university-wide resilience center, the security center called Sirius, and a GE-funded center called Priam, which is looking at data analytics at large scale coming out of all the sensors in industrial control systems. So I would categorize the work that we do in our lab in 3 broad thrusts. I'm going to discuss these in order. The first thrust is on distributed intrusion tolerant system. So our computing systems are beginning to be more and more distributed rather than a centralized single node. These are multiple nodes which cooperate amongst themselves in order to provide the end user functionality. And we need to be able to build these systems that are able to tolerate intrusions, not just detect intrusions. In other words, these systems need to be resilient to new kinds of intrusions, and they need to be able to work around these intrusions or fight through these intrusions. So maybe the functionality of these systems are going to be degraded when they are subjected to a successful intrusion, but they're not completely going to become offline. So this work encompasses 4 different phases. There is the detection phase, in which there has been a lot of prior and also ongoing work. How do you detect that an intrusion has started in the system? The next phase is the diagnosis. Can you identify, pinpoint where the current attack is? Which is the suspect flow in my system? Followed by containment. So once I have pinpointed which are the affected parts of my system, can I contain the intrusion to only those affected parts so that part of the functionality of my overall system is still available to the end user. And then finally, a response. Can I deploy a distributed autonomic response so as to either slow down the spread of the attack or contain the spread of the attack, or maybe even have attribution for where the attack is coming from. So in this broad ambit, we have come up with solutions for these different aspects. So we have an attack graph based modeling of multi-stage attacks. This is where an attack starts at one point, maybe by compromising an externally facing service, and then spreads through a step-by-step, stepping stone process till finally the crown jewel, which is far inside the system, is compromised. We've come up with algorithms for containing the spread of the attack and for real-time, semi-optimal response selection. What is the right set of responses to put in place based on evidence that we are getting from the different sensors in the system. An important challenge here is that the sensors in our system, or any system, are going to be incomplete and partially accurate. So the response determination has to be done in the face of these imperfections. And then an important challenge here is that purely signature-based mechanisms, where you say, if you see this, then do this, that does not work in practice, because you have novel kinds of attacks which come up for which see this, that exact symptom may not be programmed in or may not be known at the time of deployment of the system. So here's a very simple schematic for how an attack, a stepping stone or a multi-stage attack may spread. So here what you see is you have different kinds of servers, your web server, FTP server, your file server, database server, and then you have sensors which are deployed on some of these servers. Some of these servers are outward facing, so from the external world you can reach these servers, and some servers are inside. So by piecing together information that you get from the various sensors at the various servers, you want to be able to do those things of diagnosis, containment, and then deploy autonomously the right set of responses.